Hello viewers, today in this part of the lecture we will discuss Fraunhofer diffraction, and the brief outline for today's discussion is as follows. First we will discuss in general what is diffraction, then we will go and discuss Fraunhofer diffraction, and in there we will discuss the diffraction from single slit. Then we will discuss diffraction by circular aperture followed by two slit diffraction. Then we will discuss diffraction grating and its resolving power, and in the end we will discuss resolving power of telescope and microscope. Diffraction. So, the spreading out of waves when it passes through a narrow opening and the width of the opening is comparable to the wavelength of the wave. If these two conditions are satisfied, then we can observe a diffraction pattern, or the process is called diffraction. Now, the intensity distribution on the screen is called diffraction pattern. So, in general the diffraction is divided or categorized into two parts. The first one is called Fresnel diffraction and the second one is called Fraunhofer diffraction. So, today we will discuss Fraunhofer diffraction, and it is observed when the source and the screen are present at infinity from the slit. So, as you can see in the figure, a point source is present in the focal length of a lens L, and after the rays passes from the lens L, it will go and fall on a slit, and from the slit when it comes out, it again falls on another lens, and this slit is present in the focal length of the second lens, and after it crosses the second length, it falls on a screen which is in the focal length of the second lens. So, the Fraunhofer diffraction can be achieved by placing a source in the focal point of a lens in one side of slit. In the other side, the screen should be placed in the focal point of another lens. Now, we will discuss the Fraunhofer diffraction from a single slit. So, this is called single slit diffraction. It is observed when the source and the screen are present at infinity from the slit. A plane wave incident normally on an infinitely long slit of width b, the intensity calculation will be done at the focal plane of a lens. The slit can be considered to be consisting of equally spaced point sources. Wavelet from each point source is interfering with each other. So, as you can see in the figure, for single slit diffraction, let point sources be at A1, A2, A3 and so on at a small separation of delta. So, if the number of point source is n, then we can represent the width of the slit B is equal to n minus 1 into delta. Now, let us find out the resultant field at an arbitrary point P on the screen, getting parallel rays at an angle theta to the normal of slit. Since the source is continuous, we can consider delta tends to 0 as n tends to infinity, such that the multiplication of delta and n is equal to the width of the slit, that is equal to B. The field produced by A1 will be different than due to A2 because of the path difference. Now, let us find out the resultant field at an arbitrary point P on the screen getting parallel rays. It can be shown that the path difference A2 prime is equal to delta sin theta. The corresponding phase difference will then be equal to phi is equal to 2 pi by lambda into delta sin theta. So, the field due to A2 and A3 could be A cos omega t and A cos omega t minus phi. So, the resultant at point P will be E is equal to A into cos omega t plus cos omega t minus phi plus the higher terms till we get cos omega t minus n minus 1 phi. And one can show that cos omega t plus cos omega t minus phi and so on till cos omega t minus n minus 1 phi is equal to sin n phi by 2 divided by sin phi by 2 multiplied with cos omega t minus half n minus 1 phi. Thus, the expression for the field will be equal to E is equal to E0 cos omega t minus half n minus 1 phi, and the amplitude is then E theta is equal to A sin n phi by 2 divided by sin phi by 2. As we assume that as n tends to infinity and delta tends to 0, n into delta tends to b. Hence, n phi by 2 is equal to pi by lambda n into delta sin theta, and that tends to pi by lambda b sin theta. So, phi is equal to 2 pi by lambda into delta sin theta is equal to 2 pi by lambda into b sin theta by n, and this will tend to 0. So, we may write the amplitude E theta is equal to A sin n phi by 2 divided by phi by 2, and that is equal to n A sin pi b sin theta by lambda divided by pi b sin theta by lambda, and that comes out to be A sin beta by beta, where n A is equal to A and beta is equal to pi b sin theta by lambda. Thus, the expression for the field is now E is equal to A sin beta by beta into cos omega t minus beta, and the corresponding intensity distribution will be I is equal to I0 sin square beta by beta square, where I0 is the intensity at theta is equal to 0. The maxima of intensity can be obtained for b sin theta is equal to m lambda. Now, differentiating the equation that we obtained for the intensity, we can get the maxima, that is di by d beta is equal to I0 into 2 sin beta cos beta by beta square minus 2 sin square beta by beta cube, and that is equal to 0. And if we simplify, that comes out to be sin beta into beta minus 10 beta is equal to 0. So, the minima can be obtained when sin beta is equal to 0, and that gives rise to beta is equal to plus minus m pi. Now, let us consider diffraction by a circular aperture. So, let us discuss diffraction of plane wave by circular aperture. So, a plane wave incidents on a circular aperture and it passes through a lens whose diameter is larger than the aperture. So, the diffraction pattern will be produced in the focal plane of the lens. Now, the rotational symmetry of the system allows it to form concentric ring diffraction pattern, and these are called airy rings. As you can see in the figure, there are two different airy ring pattern due to two different values that is obtained experimentally, and it is shown in the figure in this particular slide. Now, the intensity distribution can be derived to get I is equal to I0 into 2J1, which is a function of V divided by V whole square, where V is equal to 2 pi by lambda A sin theta, and A is equal to radius of circular aperture, lambda is equal to wavelength of light, theta is equal to angle of diffraction, I0 is the intensity at theta is equal to 0, and J1 as a function of V is the Bessel function of first order. On the focal plane of convex lens, V is equal to 2 pi by lambda into A x square plus y square square root divided by f, where f is the focal length of the lens. It can be shown that the angular spread of beam is equal to delta theta, and that is equal to 0.61 lambda by d, which is nearly lambda by d. So, in general, the angular spread delta theta is equal to lambda by linear dimension of the aperture. Now, let us discuss about two slit Fraunhofer diffraction. So, here we will study the diffraction produced by two parallel slits of width b. It can be shown that the diffraction pattern is product of the single slit diffraction pattern and the interference pattern produced by 2 point sources at a distance d. So, as you can see in the figure, there are two slits of width b, and from these two slits the rays that comes out, they will go through the lens and we will obtain the field at a point P on the screen, which is located at the focal plane of the lens. Following the same steps as single slit diffraction, one can show that the field produced at point P by a single slit is equal to E1 equal to A sin beta by beta into cos omega t minus beta. Similarly, the single slit will produce E2 is equal to A sin beta by beta into cos omega t minus beta minus phi 1. Here phi 1 is equal to 2 pi by lambda into d sin theta is the phase difference between the two disturbance from the two slits. The resultant field will then be equal to E, and that is the sum of the individual field from the slits, that is E1 plus E2, and that gives us the expression A sin beta by beta into cos omega t minus beta plus cos omega t minus beta minus phi 1, which can be rewritten as E is equal to 2A sin beta by beta into cos gamma into cos omega t minus beta minus half phi 1, where gamma is equal to phi 1 by 2, and that is equal to pi by lambda d sin theta. So, the intensity distribution will be of the form I is equal to 4 I0 into sin square beta by beta square into cos square gamma. So, sin square beta by beta square represents diffraction due to single slit of width b, and cos square gamma represents interference due to the second point source. Now, if the slit widths are very small, so that there is no variation of the sin square beta by beta square term with respect to theta, in that case one simply obtains Young's interference pattern. So, the intensity is 0 whenever beta is equal to pi, 2 pi, 3 pi and so on, or gamma is equal to pi by 2, 3 pi by 2, 5 pi by 2 and so on. So, the corresponding angle of diffractions are b sin theta is equal to m lambda, where m is integer values, and d sin theta is equal to n plus half lambda, where n is again integer values. The interference maxima is obtained when gamma is equal to 0, pi, 2 pi and so on, or d sin theta is equal to 0, lambda, 2 lambda, 3 lambda and so on. So, next we will discuss diffraction grating. So, what is diffraction grating? These are large number of equidistant slits. Diffraction from these equidistant slits form diffraction grating, and the diffraction pattern is called grating spectrum. The principal maxima is dependent on the incident wavelength. Thus, they form an easy setup to determine the wavelength of a light. Now, if we have n number of slits, then for n slit interferometer, it can be so that delta theta m is equal to lambda by n d cos theta m. So, for a narrower spectra principal maxima, the value of n must be very high. The equation for the position of principal maxima is given by d sin theta is equal to n lambda, where n is the integer value of 0, 1, 2, 3 and so on. So, this gives a relationship between diffraction angle and the wavelength. If we differentiate the above equation, then del theta by del lambda is equal to m by d cos theta. For smaller theta, for a given delta lambda, delta theta is proportional to m, and for a given m, delta theta by delta lambda is a constant and is called normal spectrum. However, for large theta there is dispersion. Since delta theta is proportional to 1 by d, so smaller the size of grating, larger the angular dispersion is. Now, we will discuss the resolving power of a grating. It is the power of distinguishing two nearby spectral lines, and that is called the resolving power, and it is represented by R, and that is equal to lambda by delta lambda, where delta lambda is the separation between the two, and less is this value, more will be the resolving power. Now, here in this slide we have shown two figures where the resolving power from the grating is due to the light that is emanating from a point source, and the other one is light that is emanating from a slit. So, the figure on the left hand side represents the resolving power and the diffraction pattern on the screen after the light comes out from the point source, and the right hand side shows the diffraction pattern after the light comes out from the slit and passes through the diffraction grating. So, diffraction pattern by a polychromatic source after passing through a grating will be different depending on the light that passes through what kind of slit, that is either point source or a slit. Now, we will discuss resolving power of a telescope. 2 point sources being focused by an objective of diameter d, this is equivalent to a circular aperture. This is followed by a converging lens of focal length f. So, the 2 point sources form airy diffraction pattern. Diameter of the airy ring will depend on the diameter d, the focal length f and the wavelength of light. If the airy patterns are quite far apart from each other, then the two objects are said to be resolved. Since one can show that radius of first ring is 1.22 lambda f divided by d, so more is the value of d, better is the resolving power. And now, we will discuss resolving power of a microscope. 2 point sources being focused by an objective, and the resolving power of a microscope of an objective of radius d is the point of interest. Let P and Q are 2 point sources as shown in the figure. P and Q will form airy pattern at point P prime and Q prime if there exists no aberration due to the lens. For point P and Q to be just resolved, the first maxima at Q prime should overlap with the first dark ring surrounding P prime. Therefore, we must have sin alpha prime is equal to 1.22 lambda divided by d, and that is equal to 1.22 lambda 0 divided by n prime d, where n and n prime are the refractive index of object and image space, and lambda 0 and lambda are the wavelength in free space and in medium. Now, from the figure we can say sin alpha prime is equal to y prime by O p prime, and that is equal to y prime 10 I prime by d by 2, and that will simplify to y prime sin I prime by d by 2. Here it is assumed that sin I prime is equal to 10 I prime. This is because O p prime is large compared to d. So, combining the two equation, one will get y prime is equal to 0.61 lambda 0 divided by n prime sin I prime, and by using sine law, that is n prime I prime sin I prime is equal to n I sin I, one can get y is equal to 0.61 lambda 0 by n sin I, where n sin I is the numerical aperture. So, this is the smallest distance a microscope can resolve. So, resolving power increases with decrease in wavelength lambda and increase in numerical aperture. So, today the concepts that we discussed that can be summarized in the following few points. So, what we discussed today is the concept of diffraction we started with, and from there we categorize the diffraction into Fresnel and Fraunhofer diffraction, and in today's discussion completely we devoted the discussion to Fraunhofer diffraction, and the Fraunhofer diffraction from single and double slit was discussed elaborately, and we also discussed some of their applications. Then we discussed diffraction grating and its resolving power, and by using the concept of resolving power, we also discussed the resolving power of microscope and telescope. So, viewers, I hope today you would have liked the lecture. Thank you very much.